Okay, before I start, I think I want to talk about the schedule. Today we're going to finish the number theory, and then next time we're going to talk about the one of the encryption algorithm called the ISA. And so today's April, um, April 28th. Next time will be um, I think it's May 5th, right? Um, According to the calendar, May 5th is the last day for the class. But however, the school actually did not arrange any test. So so from May 6th to May 12th, that's the final exam period. So so technically we can still use May 12th, you know, that's the last Wednesday as the last Wednesday because it's still within the test period. Um, but hopefully we can actually complete the class on May 5th. So I don't even think we need like a 2.5 hour on May 5th. And then we're going to schedule the test again. Um, so just like the previous test, I think the final going to be you can treat final just like another one, but just cover the last couple of modules. Uh, so again, I think I'm gonna actually uh, put the test as like on remote test, so you can have a certain time windows, like 12-hour windows, so you can start your test at any time, during that window in the window time in the window. So that's the plan. So if now for next May 5th, if the if some students have a class before my class, and so you probably need to actually talk to the instructor, Professor Natasha Katonina, let her know that you have a class, and hopefully, if you have a presentation, you're probably going to present earlier, schedule earlier time to present your part of the work. Um, so we'll see. But as I said, we may not need to have 2.5 hours, so maybe we can start maybe like a 15 minutes late, something like this. Okay. So if you have any issues, just let me know. Um, so before we actually continue, let me actually summarize the topics for the last time. Um, we actually talked about the mainly the prime number. Okay. The prime number, the prime number is probably the easiest topic. It's easy to understand, you know. Even in elementary school, people actually know what is a prime number. But it's also a most difficult topics in number theory because so far people actually still know little about the prime number in terms of their distribution. You know, mostly they cannot predict any actually prime numbers based on the numbers we know, you know. So you cannot find any patterns in terms of the distribution of the prime numbers in all the actual numbers. Okay. Um, but so there are still some actually important theories in prime number. Um, so one actually term concept we learned about is if we have two numbers, P and Q, and then we define P and Q as a relatively prime, if they they don't have um, any common divisor other than one. Okay, so other than 1. So 1 is very special, you know. So 1 can divide any numbers. So 1 can divide both P and Q. So 1 is the common divisor. But 1 is so special, so we don't think about this number. So if there's no actually common divisor other than 1, then we call these two numbers are relatively prime. So relatively prime is not the same as a prime, because that means P may not be a prime, Q may not be a prime, but they are relatively prime. Okay. So for example, as far as they don't have any common factors, so they are relatively prime. And also we talk about one concept called the greatest common divisor, okay, of two numbers. So for any two numbers, you may find some common divisor, some common divisors. A common divisor is a number that can divide both P and Q. And this number is called the common divisor of P and Q. Now, the greatest common divisor is the largest common divisor between P and Q. Okay, so that's another concept. That's the greatest common divisor. And so to find all the common divisors, you can actually do this. You can factor each of the numbers. You can factor each of the numbers. And then you can find the common factors. And this basically defines the common divisor. Now, for the greatest common divisor, you just find the largest one. Now, however, try to factor a number is a very, very difficult task. We will know that, okay? So many times, people actually use a special algorithm to find, if you only want to find the greatest common divisor, not any other divisor, then there's a way to do this. And this is called a Euclidean algorithm. Okay. Okay. The Euclidean algorithm is based on the recursive approach. So what they do is, if you have a P and a Q, and then you can actually build such a relationship. So we suppose P is larger than Q, okay? Suppose P is larger than Q. So if we want to find the greatest common divisor between P and Q, then you can actually, you can actually use this equation. So that means the greatest common divisor between P and Q is the same as the greatest common divisor between Q and
Professor,
P. Model
sorry
P. Yes?
to interrupt. Are you sharing the screen or not?
I'm not seeing anything either.
Yeah, same.
Oh, sorry.
Thank you very much.
I'm glad you mentioned that. Okay. So let me actually share that screen.
See it now.
See it now. Okay, sorry. Okay, let me actually. So I haven't talked about any new topics. We just actually summarize the topics we just covered last week. So we just covered the prime numbers. Sorry, we just covered the prime numbers, and we also, introduced the concept called the relatively prime. So the prime number is the number that can divide, can be divided by 1 or itself, not any numbers. So these numbers are prime numbers. So it's very easy to understand what is a prime number, but the prime number is also very difficult number to in the research community. In the number theory, prime number is the number that it's so difficult to understand. not the definition. The definition is so simple, but in terms of the, it's so difficult to find any pattern for the prime number. So if you look at the distribution of the prime numbers, there looks like they're random. So there's no actually any kind of pattern with the prime number. So that makes it very difficult to predict, if I find a current prime number, and then what is the next prime number? Okay, what's the next, prime number? So it's so difficult because this distribution is actually kind of random, But prime number is also very important, particularly in the computer security area. So that's something we can talk about in next module. And also, the other concept that's called relatively prime is basically defined as, a number, the two numbers that they don't have any common divisor, no common divisors, except one. One is always the common divisor for any two numbers. Okay. So now the other concept that we just introduced was the greatest common divisor. Okay. So for any two numbers, P and Q, they may have some common divisors, or the numbers that they can divide both the number. Okay. So for example, if we have two numbers like say 9 and 6, and you can find some integers that they can divide both, right? Like a 3. 3 can divide both 6 and 9. And also 1. 1 is always the common divisor. But in this case, 9 and 6 are not relatively prime because they have a common divisor, which is 3. 3 is not 1. So that's why 9 and 6 are not relatively prime. They have common divisor. And there's another concept called the greatest common divisor, GCD. The greatest common divisor is the largest common divisor between two numbers P and Q. Now, in this particular case, 3 is a common divisor, and 3 is also the greatest common divisor because there's no any common divisor which is bigger than 3, right? 3 is the largest one. So you cannot find any number which is bigger than 3 and then also can divide both 9 and 6. There's no such a number. 3 actually is the largest one. So 3 is the largest one. Now, typically, if you have two numbers, P and Q, two integers, in order to find all the common divisors, you can actually factor each of the numbers. You can factor each of the numbers. Okay, you can write each of the number in terms of as a multiplications of all the prime numbers. Now you can factor each of the numbers, and then you can find the common factors, factors that appears on both numbers. So then you can find all the common factors. And among these common factors, the largest common factor or divisor is called the greatest common divisor. Okay. Now, finding the common factors are not easy job because if you try to factor any numbers, this is a lot of work. We can talk about this later. It's a lot of work to find factors of a number, particularly when the number is huge. How can you find a common number? So for example, if I give you a number like okay. Now in this case, I know one of the factor is 2, right? Because it's an even number. So the even number 2 is always a common factor. So once you got a common factor, once you got a factor, then you can divide this number. You can divide this number by the factor, and you can actually, shrink the size of the number. Now, if the number is odd number, like a larger, the one's position is 3. Now, if I want you to find a common, a factor for this number, it's really difficult. It's really difficult. Now, with the computer, you can do this. Okay, you can basically do this by using the loop. You can actually do the for loop, like you can actually test each of the numbers starting from 2. You can divide. Oh, I'm sorry. In this number, you for any other number, you don't have to, divide 2, because you don't have to actually. You can exclude all the actually even number, because they are definitely not going to have an even number factor. But you can actually try like a 3. Divide this number by 3 to see whether I can divide the number, and then divide this number by 5, by 7, by 9, by 11, by 13. So you can always divide each of the odd number. If one of the number can divide the number, and that's the factor. That's a lot of work, even with the computer, because you're gonna have to do the loop, a very large loop. So this is gonna take a long time. Now, so this is actually a tough job to factor any number when the number is huge. Now, if you try to find, give you 2 numbers that are huge number, and then you factor both of the number and find any common facts, that's a lot of work. Okay. Now, there's one particular case which is relatively easy. Now, if someone just wants you to find the greatest common divisor between 2 numbers, then you have Euclidean algorithm. Okay. The Euclidean algorithm is based on this equality. So if you have 2 number P and Q, and you want to find the greatest common divisor, and you will find out the greatest common divisor between P and Q. Now, I assume P is larger than Q. Okay. If P is smaller than Q, then you can switch the order of P and Q. It doesn't make any difference. The greatest common divisor between P and Q is the same as greatest common divisor between Q and P, right? Doesn't make any difference. So you can always assume P is bigger than Q. And then the greatest common divisor between P and Q is the same as the greatest common divisor between Q and the P modular Q. That sounds very simple equality, but this thing makes big difference, because Q is smaller than P, right? P mod Q, modular Q, it's basically is the result when you divide P by Q, and this is the remainder, right? The remainder when you divide P by Q. So the remainder, when you divide P by Q, the remainder R, this R is always smaller than Q. Okay, so Q is smaller than P, and R is the second number, P mod Q, which is R. P mod Q is smaller than Q. So you basically convert the problem of finding the greatest common divisor between P and Q to finding the greatest common divisor between Q and R. And these 2 numbers are smaller. Okay. Now, if these 2 numbers are still big, even though they are smaller than the previous 2 numbers, then you can actually use the Euclidean algorithm again, right? So you can put the second number R to the first place, and then the second number becomes Q mod R. So then you can actually shrink these both number even further. So this way, if you continue with that way, eventually you will actually turn the problem of finding greatest common divisor between P and Q into a problem of finding the greatest common divisor of 2 numbers that are very small. Then you can solve that problem. Okay, so we did that example, so I'm not going to repeat this. So you can actually go back and check. Okay. Now, one of the algorithm we're gonna use later on is to find a prime number. We can find a huge prime number. Okay. Now, how can you do this? Because even if I give you a number, it's so difficult to verify this is a prime number or not, right? Because in order to verify this is a prime number, so you have to make sure, you test all these factors, make sure none of these numbers smaller than the number is a factor of this. And then you can say, okay, this number has no factor other than 1 and itself. And then this is a prime number. By definition, the prime number is a number that can divide by 1 and itself. Now, if you can factor it, that means you can divide, this number can be divided by a smaller number. So then it's not a prime number. Okay. Now, in order to do this, you need a son of the theorem called the Fermat theorem. Okay. The Fermat theorem, I'm only listed the result over here, but I'm not going to prove it. Again, as I said, in number theory, the theory is very easy to understand, but to prove it, it's extremely difficult. Okay. So this theory says if P is a prime number and A is a positive integer, not divisible by P. So that means P cannot divide A. Okay. P is a prime number. P cannot divide A. And then we find out that the A to the P minus 1 is the same as 1 under modular P. Now this is also says, it's equivalent to says A to the P minus 1 modular P is actually 1. So this is the same statement. Okay. A to the P minus 1 modular P equals 1. If P is a prime number and the A is a positive number, not divisible by P. Now we can verify this. Okay. We can easily verify this theory. So let's actually take some example. Let me discard this. Okay. So let's see. So let's take a look at the example. We cannot prove it, but I can verify it. Definitely we can verify, and we can randomly pick 2 numbers. Let's say, suppose I pick a prime number P. P is 13. Okay. So P is a prime number, right? And I pick A, which is 14. So A is a positive integer. Certainly A cannot be, P cannot divide A, right? Because when P divides A, you have a remainder. So P cannot divide A. And then let's verify. Does that true? A to the P minus 1 modular P, is that 1? Okay, let's test it. So A is 14 to the P, which is 13, minus 1, modular 13. That sounds a lot of work, right? So then this is the same as 14 to the 12th modular 13. Now what should we do? So you need to multiply 14 12 times, right? 14 times 14 times 14, because the power is 12. So you can say 14 times 14 times 14 times 14. You need to multiply like 12 times. That's a huge number. Okay. Now with modular operation, we can actually use some kind of formula to simplify the calculation. So it's not really that difficult to calculate the result. Now, which formula we can use? Remember, if we actually multiply two numbers, say, let's say 31 times 41 modular 6. Remember, we can use one of the formula. So you can actually do the 31 modular 6 times 41 modular 6, right? And then modular 6. Do you still remember the formula? Let me actually
Yes.
show you. Let me show you this. I think, here we go. No, yeah, this one. So A times B mod n is the same as A mod n times B mod n and then mod n. So you can actually use that formula. So if you want to actually A and B are big, then you can put the mod n inside each number. So you can calculate A mod n, because A mod n gonna actually eventually make a number smaller than n. B mod n is smaller than n. So then mod n. Okay. Now, if we continue with this, then we will find out we can eventually get this formula. So so this is pretty simple. So 31 mod 6 is, let's say, 31 divided by 6, 5. 5 times 6, 31. So the remainder is 1. So this is a 1, right? Now, 41 mod 6. 41 divided by 6. 6, right? 6, 36. It's 5. So this is 5 mod 6. So 1 times 5 is 5. 5 mod 6 is 5. So this 31 mod 6 is 5. Now this is much simpler than just multiply these two numbers. And then you got a huge number. Then you can do the division and then find the remainder. That's more complicated. Now, however, now this formula can be actually extended to a general case. Okay. You can extend this one to the general case. Okay. So if two numbers are the same, say, let's say, so if I have A times A mod n, then I have A mod n times A mod n mod n, right? So you can actually put inside. And this A mod n, A mod is the same. So we have A mod n square mod n. So that means A square, A times A square mod n equals A mod n square mod n. Now, if I have multiple A, like a 3A, and then I'm going to have a 3 here. So you can actually put the 3 additional one, you have 3. So basically, A to the any number, like A to the 10 mod n, is the same as A mod n to the 10 mod n. So you can put the n inside. Now, back to this problem. So if I use this formula back to this problem, now what am I going to do? What should I do? So
14 mod 13.
so this is going to be 14 mod 13, 12, mod 13, right? So you can put a 13 inside this, and a 14 mod 13 to the 12 mod 13. Now what is this?
It's 1.
It's 1. 1 to the 12 mod 13. 1 to the power of any power is still 1. So 1 mod 13 is 1. So 14 to the 13 minus 1 mod 13 is 1. Yeah, we verified this. Okay. Now let's try another number. This is kind of fun, right? So we have a very simple way to actually modify the, let me erase these numbers. Okay, so we verified that if A is 14, P is 13, then we verified that, yeah. So if A is 14, P is 13, then we know that A to the P minus 1 mod P is 1, right? That's true. Now let's take a look at another example. So if P is a prime number, so I put a P equals 17 and A equals 28. Okay. Now P is 17, which is a prime number. A is positive integer not divisible by P. Of course, 27 cannot be divided by 17, right? Now 17 can divide 34. 17 can divide 17, can divide 34. Or 70 can divide 51, right? So, but 24 is not a multiple of 17. So in this case, the condition for Fermat theorem is true. So now we just verify, we can verify that the A to the P minus 1 modular P is 1. Now what does that mean? Which number we try to verify? So it's 38 to the 17 minus 1 mod 17 is 1. We just want to verify this, right? Again, that's a huge number. 28 to the power of 16. So you need to multiply 28 16 times. That's a huge number, okay? But we have a trick, right? So we know that the 28 to the 16, which is 17 minus 1, mod the 17. So you can actually do the modular operation, 28 mod 17 to the 16. Mod 17. So these are the same. Now this one can dramatically reduce the size of the number. So 17 divided by 28 divided by 17, what's the remainder?
11.
Okay. Yeah, 17, 11. So we can actually, now this is a very simple problem now. So we talk about 28 to the 16 mod 17. Now it becomes 11 to the 16 mod 17. But we can repeat this, okay? Now 11, 16. So we can bake 11 is less than 17. So using the same trick, it's not gonna do the work, right? So in this case, we're gonna put the 11 mod 17, 16 mod 17, and that's still 11. Doesn't make any difference. So so what we do is we're gonna do a small trick. That's what we do. Now, in one of the computer science, I ask a student to write the program to do this. So now 11 to the 16, you can write as 11 square to the 8, right? So you can split the power 16 to 2 times 8. And then you put the 2 inside and the modular 17. Now 11 squared is what? 121, right? To the 8 mod 17. And then you use the trick again because 121 is bigger than 17. So now you can put the 121 mod 17 to the 8 mod 17. Now what is this?
2.
2.
2.
2.
That's much better. 2 to the 8 mod 17. Okay. Now, this could be, let me actually continue over here. 2 to the 8 mod 17 is 4 to the 4th mod 17, right? Or 16 square mod 17, right? And the 16 is still less than 17. So I'm going to say 16 square. What's that? 256
56.
mod 17. And what is that? I know it's 1, but let's verify. Because I know it's 1 because these two numbers satisfy the condition. So it must be 1. But let's just verify. 256 divided by 17. So I have a 1, 17. So I got the 8, 86, right? So what am I going to put here? 5. 5 times 7, it's a 5, and I put 3. 1 times 7, 5 is 5, plus 3 is 85, so it's 1. So the remainder is 1. Okay. Yeah, it's 1. So at least for this number with modular operation, I can do this by hand without any help, without the help of computer. Now, if I actually, if you can write the computer program to do this trick, it will be very quick. And one advantage for this is because if you really want to multiply this out, this is going to be a huge number. Now, in most case, the computer cannot store that number, like a 28 to the 16. That number is huge. Okay. But if you think this is a huge number, you're wrong. When we actually do the computer security, the encryption, we are actually doing some number which is much, 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 much bigger than this. And in that case, it is impossible to just multiply these, things out and still can store the number in the computer. You cannot. But now with this trick, then your number is never going to be bigger than this, because every time you do the modular operation, the number is going to be reduced to something smaller than 17. And then you can actually do the trick again, so you can continue to reduce the number. Okay. So this is actually Fermat theory. Now Fermat theory has another actual variation. That means a to the p minus 1 is modular p equals 1 is the same as a to the p equals modular p equals a. Now you can think about this just like multiply a on both sides, right? So a times a to the p minus 1 is a to the p equals a modular p. So you can do this. But that's not as simple as this because the condition is different now. So if p is a prime number and a is a positive integer, then this is always true. So now the condition is weaker, right? A doesn't have to be, the second condition is no longer needed, but this is still true, okay? But just remember this Fermat theorem. And the next concept that we're going to introduce in the number theory is called Euler's Totient function. Euler's Totient function. And I use the notation phi of n. So Euler's Totient function, it's a function of a number n. Okay. Now, what the function is defined? In the Euler's for Totient function, phi of n is defined as a number of positive integer less than n and a relative prime to n. Sounds pretty complicated, right? But let's take a look at the example. Now let's find out Euler's Totient function of phi of 12. Okay. Now this first number. Now based on the definition, so Euler's Totient function is defined as the number of positive integers less than n. Okay. Now, for n equals 12, what are the numbers of positive integer less than n? All the number functions, all the number of positive integers less than n. What are these numbers? What are these integers? 1,
1 through 11.
2, 3, all the way to 11, right? Okay. However, we need to find out in this list of numbers which numbers are relatively prime to n. Okay, so let me completely write these numbers: 4, 5, 6, 7, 8, 9, 10, 11. So I need to check each of the number. Okay, so 12 and 1. So to check the two numbers are relative prime, it's easy. You just check out what's the largest, greatest common divisor. If the greatest common divisor between these two numbers is 1, then these two numbers are relative prime. So from this perspective, 12 and 1, they are relatively prime, right? Because the greatest common divisor is 1. So 1 is actually relative prime to any numbers because the 1 and any other number, the greatest common divisor is always 1. Any number then bigger than 1 cannot divide 1, right? So this is actually 1 and 12 is relative prime. And the 2 and 12,
No.
they're not, because they have a common factor 2, right? 2 can divide 2, and 2 can divide 12. What about 3 and 12? No, because 3 can divide 3, 3 can divide 3, and 3 can divide 12, right? That's a no. 4 and 12, they have a common factor, so they are not relatively prime. If they have a common factor other than 1, that's not relatively prime. Now, what about 5 and 12?
Yes.
Yes. No for 6, right? Yes for 7. For 8?
No.
No, because I can find a 2 which can divide 8 and which can divide 8 and divide 12. 9? No,
No.
because
We
3
can divide.
3 is actually common factor, right? 10? No, because you can find a 2. 2 can divide 10. 2 can divide 12. And the 11? Yes. Okay. So then, what's the number of positive integer less than n and the relative prime to n? So you have a 1, 2, 3, 4. So that means phi of 12 is 4. Okay. That sounds a lot of work, right? But in certain special case, you can easily find the Euler's Totient function for a certain special number. Now, what about the phi of 17?
16.
It's 16. Why? Because for
It-
17, it's a prime number, right? So when you say 2, 1, 2, 3, 4, all the numbers up to 16, 1 and 17, they are relative prime. 2 and 17, they are relative prime because, any number less than 17, they don't have any common factor with 17 because 17, only factor for 17 is 1 and 17. So none of these, so the only common factor is 1 between 17 and any of these number. So now how many of these numbers? From 1 to 16. So that's a total of 16. All of these numbers are relative prime to 17. So it's 16. That's a good one. It's very good to know, okay? It's very good to know. Now, what about the phi of 13, 23?
22.
22. Because if you check the 23 is a prime number, right? So Euler's Totient actually function is for 23 is 22. Now what about 35? That's a little bit complicated. So that's 4. Okay. That's a little complicated. So okay. We can actually check. Okay. We can now this number, there's an easy way to calculate this number. Okay. So let's see. Okay, I'm not going to spend time on this, but you can verify. But let's check the next property for the Euler's Totient function. Now, if p is a prime number, then you're going to see the Euler's Totient function for p is p minus 1. That's easy to understand, right? Because any number from 1, 2, 3, 4, all the way to p minus 1, all the numbers less than p, they are all relatively prime to p. So that's the total number is p minus 1. Okay. Now the second property, it's very, very good property. Okay. Now this is going to help you a lot. In many cases, it's going to save you a lot of time. So suppose p and q are two prime numbers, and the p and the q are not the same. And then phi of the Euler's Totient function of p times q is the same as Euler's Totient of p and Euler's Totient times Euler's Totient of q, function of q. And because p and q are both prime number, so phi of p is p minus 1, phi of q is q minus 1. Remember this one, okay? This is so important that we're going to use this later. Now, if you have this, then if I ask you to find out what is the phi of 35, now can you do this?
28. Yep.
You
7.
can,
7
you
in
can actually factor the 35 to be 5 times 7, right?
Yes.
And the 5 is a prime number, 7 is a prime number. So based on this property, which is again difficult to prove, but we can use it. So this is the same as phi of 5 and the phi of 7. Phi of 5 is 4, phi of 7 is 6, 24.
24.
That's amazing, right? Now, if you try to do this and from scratch using the definition, so you have to check from 1, 2, 3, 4 all the way to 34, and you check each individual number with the 35 and to see whether there's a prime number, relative prime, whether this number is relative prime with 35, whether this is relative. You need to test like 34 times whether they are relative prime. And then you can finally find out, oh, there are 24 numbers less than 35, which are relative prime to 35. But with this formula, it's just a piece of cake. We can find. We don't know exactly which number, but we don't care. We just need to know there are 24 numbers that are relative prime to 35. These 24 numbers from 1 to 34. Okay. Are you still suspicious about this result? That you can verify. Okay. It could probably take like 5 minutes. Okay. But here, I just use like less than a minute. I can find out what it is. Okay. Remember this formula. Okay. So we're going to use a good applications on this. So the next one, so basically list these numbers. So basically I list all the Euler's Totient function for the value n from 1 to 30. Okay. Now, Euler's Totient function for 1, phi of 1 is actually 1. So you can think about this as just definition. Okay. Doesn't make any, it's meaningless because, and then for 2, it's also 1 because you check the numbers from 1 to, only need to check number 1. 1 and 2 is also relative prime. So there's 1 relative prime. Now 3, because it's a prime number, right? So this is always easy. If it's a prime number, you will find it out. It's easy. Like a 3, 5, 7, 11. That's a prime number. 13 is a prime number. 17 is a prime number. 19 is a prime number. 23 is a prime number. What is that?
29.
29 is a prime number. So for prime number, so the Euler's Totient function is always this number minus 1. Okay. So we know that. Now for the other number, you have to either actually verify it, or you have to actually, find out by definition. Okay. Like a 6. So what's the phi of 6? Phi of 6 is 2. Why? Because I just check number 1, 2, 3, 4, and 5. I find out 1 and 6 is relative prime. So that's always the case. Okay. 2 and 6 is not. 3 and 6 is not. 4 and 6 is not. 5 and 6, yes. So only 2 numbers. Okay. Sorry. So this is why. So it's the concept is very simple. The Euler's Totient function is phi of n is the number of positive numbers less than n that are relative prime to n. Okay. So these are important. Now, remember the Fermat number. So now we're talking about the Euler's theorem. Euler's theorem is actually the same. It's actually the generalization of Fermat theorem. Why? Remember this. Okay. So in the Fermat theorem, it says a to the p minus 1 equals 1 mod p, right? If p is a prime number and p cannot divide a. Okay. Now, Euler's theorem use the Euler's Totient function of n. Okay. So that means that for every a and n, if they are relatively prime, a to the phi of n equals 1. Now, in a special case, When n is a prime number, when n is a prime number, so this Euler's theorem becomes Fermat theorem, right? When n is a prime number, so then a equal phi of n is n minus 1, right? When n is a prime number, if n is the prime, then a to the phi of n equals a to the n minus 1. So that means if n is a prime number, so then it becomes a to the n minus 1 equals 1 mod n. So this is actually exactly the Fermat theorem. And the same thing with this. Okay. So that's Euler's theorem. So it's generally true, but if P is not a prime, then so a to the phi of n is, modular n is 1. Okay. This is really good. Okay. So now the Fermat theorem becomes a special case. N is a prime, then phi of n is n minus 1. So that's the reason why. So you have this. You have this. A to the p minus 1 equals 1. If p is a prime number. If p is not a prime number, but you can say a to the phi of p equals 1 modular p, right? But if a p is a prime number, then you get this. So that's Euler's theorem. That's Fermat theorem. Okay. Now, with all these property, then we can actually introduce a algorithm, which is actually widely used algorithm to test a number, whether a number is a prime number. So, before we actually use the algorithm, the typical way to test a number, whether a number is a prime number, is to, do the loop, right? If I given a p, whether p is a prime number, then I divided p by 2, I divided p by 3, I divided p, oh, no, you don't have to divide p by 2. Because normally, if I give you a number and I ask you to check whether the number is a prime number or not, normally I can only give you the odd number. I'm not going to give you even number, because even number never going to be a prime number, right? So only odd number. So when I do the testing, I'm going to test, I divide the number by 3, I divide the number by 5, I divide the number by 7, divided by all the odd numbers, all the way up to the half of this number. If none of the number can divide the number, then it's a prime number. So that's called the sieve, traditional sieve, using, it's called a triad division. So, or it means, in another word, it's just basically divided by all numbers, okay, in terms less than the square root of the number. Okay. Now this only works for small numbers. Okay. Now what we try to actually introduce is using some kind of statistical primarity tests based on property of primes. Okay. Now here is the algorithm, which is called the Miller-Rabin algorithm. Okay. I listed the algorithm here, but you just take a look. Okay. You don't have to, you just need to understand what this algorithm is. Now, if someone gave you a number, n, that number could be huge. Okay. For example, n is this number. I want you to tell me whether this is a prime number or not. Now, what are you going to do? Now, this is the algorithm. So what you do is you find integer k, q, and a q. So that find the integer k, q. K is greater than 0. And the q is odd number. Sorry. So that n minus 1 equals 2 to the k times q. Now that's always easy to do. Okay, why? Now, if I give you a number, that number is always an odd number, right? Because otherwise, I'm not going to ask you to test. Like I say, when I test a primarity for a number, never give me an even number. Because even number never going to be a prime number. So it's always odd number. So let's say if I give an odd number, say 923. Okay. Now, the first step is to find the k and the q. How can I find the k and the q? So I actually do this. So n is a 923. Now, so then I do n minus 1. Okay. N minus 1 is 922, right? So it's an even number, right? So for the even number, you can actually find the even factor. Okay. Now, what is 2? What is k and what is q? So I can try it out. So what I do is I can find out how many factor 2 is actually I can find. 922 divided by 2, and I can find divide 2, so I can, there's 4, 12. Okay, so it is 2 times 461. Okay. So I find it. So in that case, what is k? What is q? Q is odd, so this is odd. So q is 461. What is k? K is 1, right? Okay. Now, once I find this, then I can select a random integer, randomly select an integer, which is between 1 and n minus 1. Now I can do the following test. If a to the q mod n is 1, then I return may be prime. So that means this number may be a prime. The n is maybe a prime. Just keep that in mind, it may be a prime. So it still could be a composite number. Okay. But I don't exclude that the probability that it still could be a prime, which is good. Now, so I return it. Now, if this test fails, the step 3 test fails. And then I'm going to do the following test. I'm going to do the loop for j equals 0 all the way to k minus 1. So in this case, k equals 0, k equals 1. So I only test for one j equals 0, because k is 1. So from j equals 0 to 0. And then I'm going to check a to the 2 to the j times q. So j is 0, so a to the 2 times j is, oh, I'm sorry, j is 0, yeah. A to the 2 to the j is 1, right? 2 to the 0 is 1. And the q is this. Mod n equals n minus 1. If that's true, then I can return maybe a prime number. Maybe a prime number. Now, if both step 3 and step 4, step 5 is successful, then I'm going to return. So I complete the test, say the test result says it's a maybe a prime. Now, if I fail both 3 and 4 and 5, then if all these tests fails, then that number is definitely a composite number. So it's not a prime number. So get rid of this number and try another number. So this is how people find a large prime number. So they randomly select an odd number, which is huge, and then do the testing. Okay, if test is successful, so that means you keep that number, but it may still not be a prime number, but it just say maybe a prime. Okay, it's probably a prime. Now then you may ask me, you may say, wait a minute, what's the point of this testing? Because if I pass the testing, I still cannot conclude that it's a prime. But I fail the testing, then I can conclude it's not a prime number. So every time when I fail the testing, then I can exclude the number. But if I actually succeed the test, it's possibly a prime number. Then you can say, I still don't know whether it's a prime number or not. It's just maybe a prime number. It's not really conclusive, right? But wait a minute. So there's actually one thing you need to realize. Every time when I choose to pick a number n, and it passed this testing, so then the probability that this number is a prime increase. Okay, the probability increase. Okay, now the next slide is going to show you this. So if Miller-Rabin returns composite, the number is definitely not a prime. Forget about this. Get rid of the number. Try another number. Now, if Miller-Rabin test is successful, and then it returns, it's possibly a prime. Otherwise, so that means it could be just a prime. It is either a prime, or we sometimes call it a pseudo-prime, which means it's probably a prime. Now, what's the probability? Okay, every time when the Miller-Rabin give you maybe a prime result, so that means it passed the Miller-Rabin test. Every time when I pass the Miller-Rabin test, then the probability that the n is not a prime is only 1/4. So that means 1/4 is 25%, right? So that means 75% of the chance this number is a prime number, and only 25% of the chance it's not a prime number. Now this is just one testing. This is just pass one testing. Now if I pass two testing, so that means I then that number is passed, right? So when I do the testing, that number is passed, and I randomly select an integer a, and I just pass the test. So then the chance that it's not a prime is only 1/4. Okay, now I just say that's promising. Let me try the test again with the same number. So then I run the test again, and this time I pick another integer. Okay, randomly pick another integer, and I still pass the testing. Then remember the probability that the n is not a prime after two tests is 1/4 sorry, this is 1/4 to the t. Okay, 1/4 to the t, or 4 to the minus t. So that means if Rabin Miller, I tested twice, tested two times, and both actually passed. Okay, so then the probability that the p n is not the prime is 1/4 square. Okay, because I tested twice, right? So 1/4 square is 1/16. Right? So that means if the Rabin Miller I tested twice using Rabin Miller, and both are successful, both returns may be a prime, and then the number is not a prime, the probability that the number is not prime is only 1/16, not 1/4, 1/16. 1/16 is much big. So if n is not a prime after second test is only 1/16. 1/16 is actually, what's the percentage? I think the percentage is probably like about 7%, right? So that means 93% of a chance that number is a prime number. Only 7% of a chance that number is not a prime number. Now what you do? Try again. I try to use the Miller-Rabin test again. Test a third time. And if the third time it still returns successful, that means it still returns maybe a prime. And then the chance that the n is not a prime is even smaller. It's a 1/4 to the 3. So what is this number? So it's a 1/4 to the 3 is 64. Now 1/64, it's the chance that the number is not a prime is only like a 1/64. That's less than 2, right? 2%. Actually 1/100th, that's 1%. So 1/64th, it's about 1 point something. Now let's continue to do this, okay? For example, if I give a number, I just try the Miller-Rabin test like 10 times. I test 10 times. And all these 10 times returns maybe a prime. So that means all 10 times the test is passed. Then the chance that the n is not a prime is 1/4 to the 10. Okay, so the probability that the n is not a prime is only 1/4 to the 10th. So the probability that the n is a prime number after 10 tests is 1 minus 1/4 to the t, right? So it's the opposite. Now what about this 1 minus 1/4 to the 10? That's definitely 0.99999. It's much bigger than this. So that means the probability that the n is a prime number is very close to 1. Okay. Now, typically after 10 tests, if all 10 tests are successful, then I'm pretty sure this number is a prime number. Okay. Even though it's still, the probability is still not 1, but it's so close to 1. Okay. What do you think about this testing? Okay. So this is how people can find the primality of a huge number. Okay. How huge that number is, let's talk about this in the next module. Okay. Now this is pretty much all the number theories we need to learn to actually start at module 10. Okay. Let's see. Okay. Okay, let's take a small break before I start the new module, because we're done with this module. So Now I think if you haven't finished the homework assignment, you can start to complete the assignments for this module. And even though I think to make everyone's life simple, the due date for all the remaining assignment are going to be the last day. Okay, so you don't have to worry about this. So let's see. Okay, so let me